when you ask to find the two Bronsted bases or acids, you first need to just take a look through the whole equation and start identifying your acids and your bases. So what we have over here is we've got that the hydrogen over here is donated. So this is a proton donor, so that's acid 1. Once it has donated that, it turns into that particular base. Over here, the ammonia is a proton acceptor, so it is a base, and once it has accepted that proton, it has turned into, that acid over there. So if I am looking for Bronsted bases, it's ammonia and hydroxide, so it is going to be D. I've got the same concentration here of 3 different solutions. This is a weak acid, and the other 2 are both strong. When comparing which of the following statements is true, that solution has got the lowest pH. Definitely not. It's probably got the highest pH, because low pH means you've got a very strong acid. The H3O solution, SO4 solution, in other words, sulfuric acid solution, has the highest H3O plus ions. That looks like it might be valid, but what about hydrochloric acid? Now, the fact of the matter is hydrochloric acid is monoprotic, while sulfuric acid is diprotic. That means that the diprotic acid is actually going to have even more H3O plus ions in solution. The HCl solution has the lowest OH minus. No, it's going to be the one with the most H3O plus that has the lowest OH minus. And this particular one is a weak acid, so it's not going to have a high Ka, it's going to have a low Ka. So B is your correct answer. Before starting any acid-based titration experiment, Jenny rinses the apparatus. Which rinsing method would cause inaccurate results? The conical flask is rinsed with a base before it is pipetted into it. The amount of base that you pipette into a conical flask is very accurate. In comes exactly 25 centimeters cubed. What if I had some extra drops over here? That would mean that this would be inaccurate, which means it might be the right answer. Sorry, it's inaccurate, but it's the right answer. The burette is filled with the acid, it is rinsed with the acid it is filled with. Well, here's my burette. I haven't run anything out of it yet, and it's got some drops of acid in there, and then I pour in a random amount of acid. That's not going to affect anything, so that's okay. It's a bit negative. The pipette is rinsed with the base before we use it. Same sort of story. Here's the pipette, and it has got drops of base in it, and then I suck up the pipette and I fill it up to that point. Really doesn't matter that there were some drops in there beforehand. The measuring takes place afterwards, so this is an okay thing to happen. And the volumetric flask, which was used to make the standard solution, was rinsed with water first. So let's look at that. Here's the volumetric flask, and I've put some drops of water in there, and then I fill it up with water. Does it matter that I had some drops of water in there first? No, it does not. So the only problem that's going to yield inaccuracy is the conical flask. We've got Ezekiel Saping, and he wants to prepare a Slomag vitamin supplement. He dissolves 0,1 moles of magnesium chloride and 0,1 moles of magnesium phosphate in water. He dilutes it to exactly 1 decimeter cubed. What is the magnesium ion concentration? So what have I got? I have got MgCl, and that was 0,1. And that means that when that splits up, it's a 1-to-1 ratio. I will have 0,1 moles of magnesium 2 plus ions. With the Mg3PO4 2, it's going to dissociate into 3 Mg2 plus ions plus 2 PO4 3 minus ions. So that means that I have got a 3:2 ratio over here, and in terms of the whole salt, for every one of those, there are actually 3 magnesiums. So my magnesium 2 plus ion concentration is going to be 3 times 0,1. And therefore, altogether, I'm going to have 0,4 moles of magnesium dissolved in 1 decimeter cubed, so that's per decimeter cubed, so D is your correct answer. Which of the following is an ampholyte? Now, an ampholyte means that it can be a proton donor or a proton acceptor. If this donates a proton, it becomes HSO4-. That seems to make sense, but we've never heard of something called H3SO4+. That is not an ion that you've ever seen. You've seen the bisulfate ion before. What about H2CO3? In other words, I have added a hydrogen to that. And if I take a hydrogen away from that, I get CO3 2-. That looks like a great ampholyte. Can either donate or accept a proton. Then you get HSO3-. That's a good ion. That's the bisulfite ion. And then, but there's no hydrogen to donate. It can't be a proton donor. Let's try the next one. We can get NH3, which is super, or we can get NH5+. That's not on our list of ions. We've never seen that in our lives, so that doesn't seem likely either. So we've only got one ampholyte there. Ethanoic acid is monoprotic. What is meant by the term monoprotic? It has one hydrogen to donate. Define an acid in terms of Bronsted-Lowry. It is a proton donor. And ethanoic acid is classified as a weak acid. What is meant by this term? It ionizes poorly in water. Or forms few ions in water. Or the equilibrium lies to the left when it is dissolved in water. Write down the following equation and clearly indicate the conjugate acid-base pairs. So this water donates a proton and becomes that base. So we'll call that a proton donor, which is an acid, and this is a base. Over here we have a proton acceptor, and it turns into this acid over here. What property of water is illustrated in this reaction? Either that it is an ampholyte, or you could have said autoprotolysis. I'm sorry, I'm not sure that I spelled ampholyte right, but anyway, autoprotolysis, self-ionization, any of those would be fine. You've got 15 centimeters cubed of this solution. It's got a concentration, sorry, that should be a -3, and it has to be titrated against an HCl solution of a certain concentration. The reaction is given, yay, they've balanced it for me. Determine the volume of HCl that is required. I'm going to use the easy formula, Na/Nb, Ca/Va, Cb/Vb, because it is possible to do it with this. So I'm going to say number of moles of acid, number of moles of base is equal to concentration of acid, 0,1, volume of acid, I do not know. Concentration of base, I do know. Volume of base, I do know, 15. And then I plug it all in and rearrange, and I find that my volume of acid turns out to be 30 centimeters cubed. In terms of proton transfer, define an acid. An acid is a proton donor, and a base is a proton acceptor. Solutions of nitric acid and ethanoic acid. Nitric is strong, ethanoic is weak, have the same concentrations. How do their pH values of these two solutions compare? Explain your answer. Well, this nitric acid will have a lower pH than ethanoic acid. Why? Because nitric acid forms lots of ions in solution because it is a strong acid, whilst ethanoic acid forms few ions in solution because it is a weak acid. We've got, that question's already done. Tabo and his friend David were enjoying their neutralization experiments. They dissolved a certain amount of oxalic acid in water and added more water till they got a certain volume. Calculate the concentration of the oxalic acid. So the first thing you're going to do is you're going to say number of moles is equal to mass over the molar mass of oxalic acid. And you get 126 as the molar mass of oxalic acid, and my number of moles will then turn out to be 0,018 moles. I have to dissolve that into 250 centimeters cubed, so concentration is number of moles over over volume, which is 0,018 divided by 0,25. I have to go into decimeters cubed because I want a concentration in moles per cubic decimeter. So I get 0,071 moles per cubic decimeter. That's the concentration first. What volume of this solution of oxalic acid would be made up by Talbot to give him 250 centimeters cubed of that concentration. So now we've got a dilution that we need to do. So when I've got a dilution, I'm going to take the one that I know everything about, that's that container, and work out my number of moles. My number of moles is equal to concentration times volume, which is 0,05 times by 0,25. And I get 0,0125 moles. Where did that come from? It all came from this container over here. So I've got a number of moles, 0,0125. And I am asked to work out a volume. Volume is equal to number of moles divided by concentration. So it's 0,0125 divided by 0,071. And I land up with 0,176 decimeters cubed, which is really 176 centimeters cubed. So I need to take 176 centimeters cubed, and to that I need to add another 73 centimeters cubed of water, and then I will be up at 250 centimeters cubed of this solution over here that we were trying to make. So the question was what volume of this solution, so it's 176 centimeters cubed, should be made up to give that. So I would take 176 centimeters cubed, put it in the volumetric flask and fill it up, and I would have the perfect number of moles. During David's titration, 22 centimeters cubed of that solution of oxalic acid was needed to neutralize 20 centimeters cubed of sodium hydroxide. They give me a balanced equation. It's a 1:2 ratio, and I'm going to go number of moles of acid over number of moles of base, concentration of acid, volume of acid, concentration of base, volume of base. Number of moles of acid is 1 from there, number of moles of base is 2 from there, and that is going to be equal to, they're giving me a concentration of oxalic acid at 0,05. David uses 22 centimeters cubed of that, so I'm going to put a 22 in for the volume of acid, and he used 20 centimeters cubed of base, and we don't know the concentration of the base. We need to work out the concentration of sodium hydroxide, and it turns out to be 0,11 moles per cubic decimeter. Which indicator would be best for this experiment? Well, we've got a strong base, sodium hydroxide, and a weak acid, organic acid, which is oxalic acid, and therefore we're going to get a basic endpoint, and therefore we would use phenolphthalein.